Okay, picture this scenario. You're a clone trooper in the Grand Army of the Republic. You're standing in formation, right? To your left is the guy who shares your exact genetic code. To your right, another guy, same DNA. Now, let's say your battle buddy drops his data pad. You pick it up. Could you unlock it with your thumbprint? Or think about Fred and George Weasley from Harry Potter. Could Fred frame George for a prank by leaving his fingerprints on a firework?
I hate to be the guy who ruins a great sci-fi plot right at the start, but no, absolutely not. You couldn't unlock that data pad, and Fred would definitely get caught.
Well, hold on. They're identical. We're
But
talking same DNA, same face, same everything. I always thought DNA was the instruction manual. If you have the same blueprint, you get the same building, right?
you'd think so, but biology is messier than construction. It's
Hmm.
more of a conversation between the blueprint and the job site. And if we look at the source material for today, especially the exhaustive literature survey on human fingerprints, it's crystal clear. Even identical twins who share, 99.97% of their DNA do not have the same fingerprints.
Wow, that is genuinely hard to wrap my head around. So if the code is that similar, where does the difference come from? Welcome to the Deep Dive Lab, everyone. Today, we're solving the mystery of uniqueness. We've got a stack of research here, that big survey, plus studies from journals like Cell and PNAS. Our mission is to figure out that tug-of-war between genetics and what you called biological noise.
That's exactly what it is. It's a battle between strict rules and total chaos.
Biological noise, it sounds like a mistake, like static on a radio.
In a way. But let's start with the genetic rules before we get to the static. You ask why the building isn't the same. Well, the DNA blueprint, it only gives instructions for the general shape of the building, not, where all the furniture goes.
So the fingerprint pattern, the loops and the swirls, that's the furniture.
Not quite. The survey points out that while the prints don't match, identical twins very often share the same class of patterns.
Okay, define class for me here.
We basically sort fingerprints into three main types: arches, loops, and whorls. And the research shows that in one big study, about 74% of identical twins had the same pattern class on the same fingers. Compare that to unrelated people, and it drops to, 32%.
So if I'm a clone and I have a whorl on my left thumb, my clone brother probably has a whorl there too.
The odds are extremely high, yes.
Yeah.
And that similarity all comes down to something called the volar pad.
I saw that term in the papers. It sounds like something from a sci-fi movie. What is a volar pad?
It's a temporary thing in the womb. Between weeks 6 and 10, the fetus gets these little swellings of tissue on the fingertips. Think of them as tiny, fluid-filled pillows.
So before we have fingerprints, we have finger pillows. I like that.
Exactly. And the size and shape of those pillows, that's all genetics. The survey mentions specific genes like EVI1 and WNT5A, which control limb development. They decide if that pad is going to be high and round or maybe low and flat.
And I'm guessing the shape of the pillow dictates the shape of the print.
It dictates the terrain. Let's say the volar pad is a hill. If it's a high symmetric hill, the ridges that form later will circle that peak, and that gives you a whorl.
That makes sense, like contour lines on a map circling a mountain.
Exactly. But if the pad is asymmetric leaning to one side, the ridges flow down the slope. That's a loop. Loops are actually the most common. About 60 to 65% of people have them. And if the pads are low or almost flat, you get arches.
So twins have the same DNA, so they get the same shaped hills on their fingers.
Correct. The terrain is genetic. That's why the class of pattern is so often the same. But, and this is key, the map is not the territory. Just because the hill is the same shape doesn't mean the trees grow in the exact same spots.
Okay, I see the split. But what actually draws the lines? We have a hill, but what's the ink?
I was reading that 2023 study in Cell, and it mentioned a Turing pattern. That's Alan Turing, right? The code break.
The very same. Back in 1952, Turing proposed this mathematical model to explain how patterns in nature like zebra stripes could just emerge on their own. He called it a reaction-diffusion system. That sounds super technical. How does that work on my thumb?
The Cell study basically confirmed this is what's happening. Imagine a chemical war happening on your fingertip.
A chemical war. Okay, who's fighting?
There are three main players. First, you have WNT. Think of WNT as the activator. It tells skin cells, grow, make a ridge right here.
So WNT is the gas pedal.
Right. But if you only had the gas pedal, your whole finger would just be one giant ridge. So WNT also triggers its own enemy, BMP.
And let me guess, BMP is the inhibitor.
It's the brake. It tells cells stop growing here. That creates the valley, the groove between the ridges. And here's the brilliant part of Turing's idea. The inhibitor, BMP, moves faster than the activator.
Wait, why does the speed matter?
Think of it like a tiny forest fire. That's the activator, wants to spread. But as it burns, it also launches little water balloons, the inhibitor out ahead of it. The water balloons travel faster and farther than the fire. So the fire burns a spot, making a ridge, but the water soaks the ground around it, making a groove where the fire can't spread.
So you get a stripe of fire, a ring of water, and then farther out, the fire can start again.
That's how you get a repeating pattern. Ridge, groove, ridge, groove. And to keep it all organized, a third chemical the study found is called EDAR.
EDAR, what does that one do?
EDAR is basically the spacer. It fine-tunes the width and spacing of the ridges, making sure you get nice, even stripes instead of, say, polka dots.
We could have had polka dot fingerprints.
They've tested this in mice. If you mutate the EDAR gene, the pattern breaks down into spots. But in us, those three work together. WNT pushes, BMP pulls, and EDAR organizes.
That's amazing. So the genes just start the machine and the math does the rest. But that brings us back to the clone problem. If the genes are the same, the chemicals are the same, the reaction should run the same way for both twins.
It should. Right. If you run the same equation twice, you expect the same answer.
So why don't we get it?
Because the equation isn't running in a vacuum. It's running inside a living womb. This all goes down during the critical stage, between weeks 10 and 16. And this is where the twins diverge, because of something called stochastic resonance.
Stochastic. That sounds like a fancy word for random.
It's a bit more than just random. Think of it like this. If you flip a coin 1,000,000 times, you know you'll get roughly 50 heads and tails. That's predictable. But you have no idea what the next flip will be. That's the stochastic part.
So there are millions of tiny coin flips happening in the womb.
Exactly. And the exhaustive literature survey points to what these are. We're not talking about big things. We're talking tiny micromechanical forces.
Like what? What's a micromechanic that can change a fingerprint?
Okay, get this. The exact viscosity, the thickness of the amniotic fluid. It's not perfectly constant. As the fetus moves, the fluid flows over the fingertips.
And that flow actually puts pressure on the skin.
A tiny amount of shear stress, yeah.
Yeah.
Now think about those Turing waves of chemicals spreading across the skin. If the fetus presses its thumb against the uterine wall, or just curls its fingers, that tiny physical pressure can slightly change the path of a wave.
So if one twin is just a little more active than the other, that physical stress can change where a ridge decides to end or split.
That's it, exactly. Those little details, ridge endings, bifurcations where a line splits in two, we call those minutiae. They are the result of that perfect Turing pattern colliding with the physical chaos of the womb.
It sounds like the butterfly effect. A tiny change in pressure on day 42 causes a completely different pattern by day 50.
That's a perfect way to put it.
Yeah.
The mother's blood pressure at a given moment, the exact rate the volar pads shrink,
Hmm.
all of it creates a unique stress map on the skin.
Okay, but what if I eliminate the chaos? Let's say I'm a mad scientist. I put two clones in identical artificial wombs. I control everything. Do I finally get matching prints?
The science says no. You would still get different fingerprints.
Really?
Because you can't control what's called molecular randomness. At the cellular level, molecules are just bouncing around because of thermal energy. The exact millisecond a WNT molecule hits a receptor is pure chance. When you scale that up across billions of cells, those tiny random variations amplify.
So uniqueness isn't an accident. It's inevitable.
It is baked into physics. Any system complex enough to build a human has enough inherent noise to make them unique.
Wow. That's pretty deep for a conversation about thumbs. Which brings me to a practical question. I have to bring up Men in Black. You know the scene where Will Smith gets his fingerprints burned off?
I was waiting for that one.
It's a classic. But is it possible? Can you just erase the chaos?
You can try, but biology is incredibly resilient. The survey has a whole section on this. Your fingerprint pattern isn't just on the surface layer of your skin.
It goes deeper.
Much deeper. The actual blueprint is anchored at the epidermal junction. It's about 1.5 to 2.5 millimeters down.
So it's like the foundation of a house. You can repaint the walls, but the foundation is still there.
Perfect analogy. If you get a cut or a scrape, as long as you don't destroy that deep junction, the skin just regenerates using the original template. The ridges grow back exactly as they were.
So for it to work, Will Smith would have had to burn his fingers really, really badly.
Deep third-degree burns. And at that point, you're not erasing prints, you're creating massive scars. And here's the irony. A scar pattern is also unique.
Right, so you just trade one unique identifier for another, probably more obvious one.
Exactly. And your prints are incredibly stable over time. There was a 2015 PNAS study that followed 15,000 people for 12 years. The match scores were rock solid. Your prints don't change as you age. The geometry is locked in.
I have to ask, though, we say unique, but there are 8 billion people. What are the actual odds of two people having the same print? Just by sheer luck.
That question goes way back. We have a source here. What is the chance of people have the same finger? A guy named Sir Francis Galton back in the 19th century estimated the probability at about 1 in 64 billion.
1 in 64 billion. But there have been more than that many people in history, right?
Estimates are around 110 billion humans have ever lived. So you might think, aha, a match must have happened.
Yeah.
But Galton's number was a very early estimate. Modern models put the odds as astronomically lower.
So, less likely.
Much less likely. Some models say it's effectively zero. The number of variables is just too huge. The universe won't last long enough for a duplicate to appear by chance.
Even with AI generating fake fingerprints, I see that in the news.
That's a different problem. AI can create a master print, a fake pattern that might fool a cheap sensor. But finding two real people with the same print, it's never happened. Modern AFI systems used by law enforcement can easily tell identical twins apart.
Because the computer isn't looking at the general pattern.
Right. The computer doesn't care if you both have a loop. It looks at the specific coordinate where a ridge splits. To the algorithm, if that point is off by a fraction of a millimeter, you might as well be a cat and a dog.
It's amazing. We think of noise or flaws as bad things, but here, the glitches, the random bumps and splits are what create our identity.
That's the beautiful part. The perfect genetic plan gives you the canvas, but the so-called imperfections provide the signature.
Okay, let's bring this all home. We've gone from Star Wars to chemical wars. If someone listening needs the short version for why their twin can't unlock their phone, what are the 3 big takeaways?
Okay, let's boil it down. Takeaway 1. Genetics provide the theme. Your DNA and those volar pads give you and your twin the same general type of pattern, the same landscape.
The theme is the landscape. Got it. Takeaway 2.
Chemistry provides the ink. That Turing reaction, the WNT and BMP chemicals fighting it out, that's the mechanism that physically draws the lines.
The theme and the ink. Okay, and number 3 has to be the chaos.
Number 3, chaos provides the signature. The fine details, the minutiae, are created by random pressures and fluid movement in the womb during that critical 10 to 16-week window. That's what scrambles the details and makes every single print unique.
Chaos is the signature. I love
Sure.
that. It really makes you think about what self even means. We say, oh, it's in my DNA, but really the DNA is just the opening act.
It sets the stage, but the performance is improvised.
Which leads me to the big question I want to leave everyone with today. We've established that your physical identity, down to your fingerprint, is shaped by random noise in the womb. A little pressure here, a bit of fluid there, and poof, you're unique.
Well, the role of the biological dice.
Exactly. So, if our physical identity is shaped by random noise, how much of who we are, our personality, our quirks, our talents, is also just the result of a random biological roll of the dice? Are we designed, or are we just a collection of beautiful accidents?
That's something to stare at your own hands and think about.
Thanks for visiting the Deep Dive Lab today. If you enjoyed this journey into the chaos on your own fingertips, please hit that subscribe button. We have plenty more mysteries to solve.
Stay curious.
We'll see you next time.